Hello folks, this video deals with my attempt to install and operate a older R22 based heat pump system, first using R290 and then later R438A Refrigerant as a substitute for the R22. I'm going to talk about such subjects as superheat and subcooling. And for those of you who may not have a good grasp of those terms, and in fact I think that may include myself. But anyway, those of you who are well versed may want to skip around a bit and not listen to me drone on about those subjects. Early in 2013, I was given a salvage split heat pump system. I decided this unit might make a nice system for my newly constructed shop. What could be better than having a free heating and air conditioning unit? The floor area of my shop was slightly less than 1,000 square feet. So I thought that a 3-ton unit might be really a good match for that unit. The furnace unit that came with the system was a vertical design that was designed to set up on the floor. This unit looked a bit worse for wear, and I preferred to have the air handler hanging up horizontally so it wouldn't take up floor space in my shop. So I scrapped the old air handler and purchased a new Goodman 3-ton rated horizontal air handler to mate up with the Fedder's outdoor unit. The new air handler is designed for use on 410A, but was modified with a thermostatic expansion valve intended for use for R22 or 47A. So I installed the equipment, gassed it up with R290, and to the best of my recollection, I just pumped down the system, adding R290. The system was started and charge was adjusted to the vapor line to approximately 64 psi. According to the published pressure temperature table, the indoor coil should be operating at about 40 degrees. The system was kicking out cold air, so I was happy. Now here is a video clip showing the unit as it is actually installed in my shop. What you see here is my 3-ton air handler. It's mounted horizontally. On the left-hand side there is some styrofoam, which is a temporary duct that was put on the end of the machine, the discharge end of the machine, to help straighten out the airflow, to make airflow measurements a little easier. The side panel has been removed. You can see on the left or the right hand side, excuse me, of the A coil, and you can see the distribution tubes. We'll climb the ladder here and try to get a little closer look at this. Right here my pointer is resting on the expansion valve, the TXV. It goes through the metal wall and comes out into, once it passes through the expansion valve, it passes through into this black insulation here and is distributed to the coil with 6 small tubes. These tubes here are delivering refrigerant first to the bottom and to the top of the coil. So once the refrigerant enters the coil, it travels through the tubing up to the top of this half of the V, and then larger diameter tubes are the return lines, and there are also 6 of those return lines. They're manifold together and they come out into the vapor hose, or the vapor line I should say, which you see right here. There are, as this refrigerant, let's say it's injected into the top row of pipes, and you see comes out, goes through all the way through this coil, it comes to the other side. Right here at about the center there is a crossover. For some reason the refrigerant that's traveling through the upper part of the coil is now shifted and makes the remainder of the trip in the lower coils. It's kind of a switch over, and there is the same arrangement, but it's not visible because it's hidden by this insulated tubing insulation over the supply tubing. This is basically as I understand, this would be called a 3-row coil, and by 3 rows we mean that there is a row of tubes that go horizontally across the coil here, and then a second one here in the middle, and the third one in the bottom, making the 3 rows. There are 16 tubes in each row going across from this side to the other side. Then there's a U-turn and the refrigerant comes back. So it's this is a standard design A coil. However, the A coil is turned on its side, and so it's kind of in a V shape. The actual coil is in a sort of a V shape, with this being the lower part of the V and this up here being the upper part of the V. I'm looking now at the outdoor unit. There's nothing really special about the installation. It's again, it's a Fetters 3-ton unit with a SEER of 12. The wood platform is just protection from the refrigerant lines that are running across. On the left side you see I have placed the aluminum cooking pan. This pan is the one that I used to collect the condensate to estimate what the latent loading on the unit was. What you've seen in the previous clip is a Fetters CH1236. The 12 stands for seasonal efficiency rating of 12, and the 36 is for 36,000 or BTUs, or a 3-ton unit. Which, based on the serial number of the unit, I believe that unit was built in approximately in April of 2008. The indoor unit is a Goodman RARUF 36B14 multi-position air handler, which I purchased in 2013, and this system was made operationally in approximately 2013. At that time in my life, I wasn't spending a great deal of time in the shop, so any shortcomings of this system were not immediately aware to me. However, during the pandemic, I began to spend a good deal more time in the shop, and I noticed the system was not doing a good job of cooling. When the temperatures, particularly if the temperatures got up into the mid-90s, I was also experiencing a freeze-up issue with the indoor coil, and I repeatedly checked the vapor line pressure and made adjustments in the system charge, but nothing seemed to help. So I decided that I needed to take a closer look at this system and see in more detail just what was happening. My first effort was to estimate the output of the system, and I used a velocity meter to determine the velocity of the air entering the machine and coming up through it, knowing the area of the entry and its velocity, then I could convert that into cubic feet of air per minute. Once you know those characteristics, you can calculate the sensible heat output of the unit using this relationship, which comes out in BTUs per hour. 1.08 times the CFM, which stands for cubic feet per minute, times the temperature difference between the inlet and the outlet. In other words, the temperature difference between the air entering the unit and the unit exiting the air unit is what is in this feature. Now you notice I used the word sensible cooling. Is there such a thing as insensible cooling? Well, I don't know, but what I mean by sensible is the heat taken from the air as it passes through the air handler to drop the temperature of the delivered air. There is a secondary event going on as the air travels through the machine. There's moisture in the air, and as the air is cool through the air handler, water vapor condenses into a liquid. The energy required from the condensate is called latent cooling. The condensing of the water vapor requires energy from the HVAC system. It turns out that every pound of condensate requires 970 BTUs. So, if we collect the condensate for an hour, weigh it, we can calculate the latent loading on the system. That calculation should be in pounds per hour times 970, or this relationship right here. The total load on the machine, the total cooling output on the machine, is a summation of the sensible and latent cooling. My first testing of the system indicated an output of only 9,137 BTUs of sensible heat. I didn't bother with the latent capacity. Usually the latent capacity may add 10 or 30% more load depending on the humidity of this air, but I was a long ways from the 36,000 BTUs that I was expecting from the machine. Now this exhibit I have here was actually copied from a book called Refrigerant Charging and Service Procedures for Air Conditioning. This is a great reference and was prepared to teach HVAC technicians the detail of the trade. I obtained the book containing this exhibit from Amazon, and I recommend that anybody who is interested in learning more about the nuts and bolts of air conditioning get a copy of it. Let's concentrate for a moment on the right side of this schematic or exhibit. And it shows the air handler with the indoor coil. There is a metering device, which is right here, which sometimes is just a slug of copper with a hole drilled through it, but in this case it's shown as a TXV, or a thermostatically controlled expansion valve. Now the tube here, the pipe or tube coming in here, is the high pressure refrigerant, liquid refrigerant. It might be running 150, 200 psi, maybe more. And as it passes through the TXV, pressure is reduced, and this refrigerant attempts to flash into a vapor. Now the dark blue area indicates where we have a combination of boiling refrigerant, meaning there's a combination of both vapor and liquid refrigerant. The light blue area is supposed to indicate where the refrigerant has completely turned to a vapor. Now I have a label on this schematic right here. I just penciled in PV, and that stands for the temperature, or excuse me, the pressure of the vapor line, and is basically measured at the service valve located right here at the outdoor unit. Right here I also have another scribble which called TSI, which stands for the saturated temperature of the inside coil. I mean inside, S means saturated, and this portion of the coil is very important because this is where the main cooling effect occurs. If the temperature is too low in this area, then the coil will freeze. This portion of the saturated portion of the coil, the dark blue area, the temperature is pretty much consistent from the bottom to the top, because what's happening is as the air passing through the coil is boiling the refrigerant, and the refrigerant is holding this temperature pretty constant. But once the refrigerant gets into the situation where it's all vapor, then that portion of the coil, the temperature can rise as you go up toward the top. Now usually this temperature is measured here again at the valves. The temperature, this TV, the temperature at the surface of the tubing is usually very close here and here, because this line is almost always insulated. Well, how do I get this temperature TSI? Well, once you know the pressure inside the evaporator, you can enter into a pressure temperature table published for the refrigerant that you're using and just look it up. Now again, I referred to TV here, and let me make sure I've defined that as being the surface temperature of the vapor line, and it's very close to the temperature of the vapor passing through it. Now if you subtract TV from the saturated liquid temperature of the indoor coil, you get what is called superheat. And in other words, if the surface temperature TV minus the saturated temperature is a number called superheat. So that TSI is a temperature right in this area of the coil, which is pretty uniform, whereas TV is the temperature of the surface of the line as it exits the coil, either here or here. Usually those numbers are essentially the same if it's properly insulated. A large superheat number as compared to a small superheat number means more of the coil is filled with boiling refrigerant. Maximum efficiency would be that the coil would be completely full of boiling refrigerant. However, this is dangerous because it's possible that you will begin to pull liquid refrigerant through the suction line into the compressor, and that is a possibility for causing damage to the compressor. So you always want to run your systems with some superheat. Usually the manufacturer will have some data for the installer to follow, giving the recommended superheat. If the indoor unit is equipped with a TXV, which our drawing shows here, the superheat is automatically controlled, assuming the system is properly charged. If the upper part of the evaporator coil has only vapor in it, the temperature of this portion of the coil will climb above the temperature of the saturated portion. In other words, this temperature is almost guaranteed to be slightly higher than this. And again, we'll get back to the concept of superheat. There's at least one other factor of operation of the HVAC system that needs to be monitored. On the left side of the schematic is located, again, the outdoor unit. The compressor, shown here in white, discharges in a dull red color into the top of the outdoor coil. As the refrigerant moves down, it's rapidly condensing, and hopefully by the time it gets to the bottom of the coil, it's fully liquid. Now, it's important that this be completely condensed, because if you have a mixture of vapor and liquid passing through this line going to the coil, you have increased friction loss in the line itself due to the space taken up by the vapor, and also the TXV, or the metering device, is usually not designed to handle a mixture of vapor and liquid. Sort of similar to what we were discussing before, I have a label here which I've called PL, which stands for the pressure inside this condensing coil, and it's usually measured here at the exterior valve. Also, I've referred to something I called, just labeled as TSO, and TS sub O is the saturated temperature of this coil, of this condensing coil. Now, that temperature is pretty much uniform from the top down until you have nothing but liquid in the line. Once that temperature stays constant, because all the air or all the heat that's being liberated into the space is going into turning this back into the liquid. But once it's a liquid near the bottom of the coil, then it can cool below this TSO temperature. And I have called the surface temperature of the liquid line TL. And usually that TL is measured outside the condensing unit, or the outdoor unit, right in this area here where the service valves are at. So we have a term called subcooling, which is the difference in temperature between the saturated portion of the coil, called TSO, and TL, which is the surface temperature of the liquid coming out of the machine. This number is an indication of whether or not this has been turned completely into a liquid before exiting the machine. And usually for air conditioning small system operation, this difference in temperature, this subcooling, is somewhere in the 8 to 14 degree range, depending on the loading and the machine design. In my unit, I was seeing a subcooling figure in the 14 to 19 degree range, and the superheat was really high at 42.9 degrees. Now, there's no ductwork on my machine, so I could, in other words, I could actually reach right in and use a infrared thermometer and check the surface of the temperature of the coil as I move from the bottom to the top. In the case of, again, of my unit with a TXV in place, the surface temperature took a jump when I'd only moved about 25% of the way up from the bottom of the coil toward the top. Now, this meant most of my cooling coil really wasn't doing any cooling because, again, as I said before, the cooling occurs where the refrigerant is being evaporated, and there's very little, if any, cooling that goes on once the coil is completely full of vapor. So only the first 25% or so of my coil was involved in the cooling operation, and it suggested maybe I had a problem with my TXV. I decided to remove the TXV and installed in place of the TXV a .078 piston. Again, the piston, now there's no automatic control here. It was just a slug of copper that gets inserted in the line here, and it with a hole in it that's .078 inches in diameter. When I checked the sensible output, I was disappointed because it had actually gone down a bit. After completing this test, I removed this piston, this .078, and replaced it with a .082, and then finally replaced it again with another piston that had 0.109 inch piston. Here is a table where I tried to condense 20 or 25 pages of just hand scribbled notes into a table to kind of summarize what my test results were. And I start here, well, back in July 17th or 15th, excuse me, and then I had one earlier one up here that I didn't record the date. Obviously my handwritten notes were not as complete as I would like on some occasions, but here in this upper portion where we're using our refrigerant R290, and this shows the various results of my tests. The ongoing problem that I was having with this was that that as the unit operated, it would start out just fine. Everything seemed to be okay, but within an hour, hour and a half, the saturated temperature of the expansion valve or the expansion coil would continue to drop to the point that it would go to cold enough to begin to freeze, and the coil freeze up. In fact, this first line across here, my saturated temperature here would start out maybe at 50 degrees and then slide down to 28, 29, well below freezing, and pretty soon the coil would freeze up. And again, I tried to adjust the charge. Nothing seemed to help, and I assumed that my TXV was not working properly, so I decided to replace it. And the first change I made was to replace it with a piston, and that piston had a hole in it. The diameter of the hole in it was .078 inches. And immediately I got a suction temperature below freezing, so I knew that wasn't going to work. So I went back, pumped the system back down, and replaced it with another piston that had a .02 hole through the piston, and I got a sensible output of 15,751. Now you notice I don't have any latent figure here because it was running so low. I didn't think it was worth the time to bother trying to estimate both the sensible and the latent load until things begin to work a bit better. I did see some improvement. First of all, started out with only about sensible of only a little over 9,000, And then with this, again, it actually slid a little below when I took the TXV out. And then when I got up to a 0.82, I was, getting up, what is that, about 19,000 BTUs. And then finally I decided to kind of go for broke, and I drilled out one of the pistons to a 109 inch diameter hole, and again, to get a respectable, sensible output. So at this point I began to weigh the amount of condensate I was getting. I would collect condensate for 15-20 minutes, and then weigh that condensate, and then extrapolate that into an hour, and from that, assuming I had so many pounds of water being produced per hour, then I could estimate what the latent heat was. And you see, I was beginning to get figures around 22,000-24,000 BTUs. I was trying various things through here, things were getting better, but I still was way short of my 36,000 BTUs total. And I kind of noticed that at times my saturated temperature seemed to be sliding up in the 45-48 degree range, and I had suspicion that saturation temperature was even warmer, because I had done a check on my pressure gauges that I was on the set of gauges that I was using, and I believe that my low pressure gauge is actually reading somewhere between 6 and 8 psi lower than the actual temperature in the system. So this saturated temperature in here, I became very suspicious that it was actually running warmer than what I indicated here on my tables. So of course, this refrigerant is R290, is propane. It is flammable. As I've said, I wasn't too worried about that in my shop, as say compared to my home, but I decided, I had a cylinder of R438A, so I decided to switch over, and I also at the same time bought a new TXV, a new 3-ton TXV, and that came into effect right here on the 25th, and you can see that again I was getting around 23,000, 24,000 BTUs of output from the unit, still way short, and I was trying some various things with this TXV. So I decided to go for broke, and I put a 5-ton TXV in here. And again, the output, the total output really didn't climb. I didn't do any better, and I began to kind of worry, because I was starting to get a subcooling here down in well below what the manufacturer recommended for this unit. And so I thought, well, I'll go back to my new TXV, my new 3-ton TXV. Here on the 913 is, I went to the new TXV, again still using the 438, and I began experimenting with trying to get the subcooling, the superheat, more or less in line with what the manufacturer recommended, while trying to keep a fairly close look on the saturated temperature, because obviously if my coil got too warm, I would not get a good heat exchange between the incoming air coming through my air handler. Couldn't get it cooled enough if the suction temperature became too high. Now, the manufacturer recommended that the subcooling, well, first of all, they recommended that you charge your system based on a subcooling rather than paying too much attention to the superheat. And they recommended that at, well, let's say at 60 degrees outdoor temperature, 12 degrees of superheat, going up to a little over 14 degrees superheat at 110. So, and this last one, I do have the superheat here at 13.1, pretty much in range. My superheat is a little high. Again, my subcooling is pretty good. My superheat is a little higher than I'd like. I did go in, I have a column here I call the saturated coil, the percentage of saturated coil that's being used. In other words, what I did was go in, measure the surface temperature of the coil as I made my way up the coil from the base upward, and then estimated what I thought the percentage of the coil that was full of refrigerant that was boiling. In any situation here, we have a portion of the coil that has a combination of liquid and vapor, and then as it all turns into vapor toward the top of the coil, then that temperature is going to climb where it'll stay fairly stable in the portion of the coil where there's a mixture of both liquid and vapor. And so the best situation, of course, is to have this 100%, the coil 100% full of boiling liquid. However, you really don't want to operate that way because there is a possibility with shifting operating conditions that you could begin to suck liquid freon back into your compressor and cause damage in the unit. All of this, well, I don't know, 20-something tests here that I've recorded on this paper, it just seems as though I'm sliding in the 22 to 25,000 BTU output, around 2 tons. And almost any amount of changes I make, I'm just not reaching my rated capacity of around 3,000. So what's the issue? Could it be that the reduced capacity is a result of wear and tear on the old outdoor unit? While scroll compressors have a number of failure modes, my limited search of the internet and other sources have not indicated that reduced compressor capacity or flow capacity of the unit is typical failure mode for the scroll type compressor. I may be wrong, maybe it does happen, but thus far I haven't found it. So at this point, I don't hardly think that's really the problem with my capacity loss. Could capacity loss be the result of mispairing of the Goodman indoor unit with the Fedders outdoor unit? Well, the box size of the Fedders and the Goodman air handlers are almost identical. Perhaps the Goodman is just a tad longer. I have not been able to find data on the A coil to check to see if they have the same square footage of coil, but at least on the surface, at least at this point, I'm not sure that I think that is an issue. Now, again, I will mention that the Goodman unit was listed and rated for operation on 410A, but it was equipped with a TXV that is designed for R22 or 407, and the R438A is supposed to be a direct drop-in substitute for R22. in your system. The printed literature for the outdoor units that the nominal capacity is 34,000 BTUs per hour, not 36,000. Now the extended printed data, again from the manufacturer, shows that a combined coil and outdoor unit has a output capacity of 36,000 BTUs up through an outdoor temperature of 95, but then begins to drop down to, well, the last one listed was 32,500 when the outdoor temperature reaches 115. Also using first using R290 and then R438A Refrigerants, I found two articles by Copeland, who manufactures a lot of these compressors. In one article, they listed the capacity of their compressor using R22, and in the second article, they listed the capacity of the compressor using 407C. Now, the capacity using the 407C was about 14% lower than using R22. Now 407 is not 438, but perhaps some of this capacity loss could be blamed on the refrigerant switch out. For instance, say 34,000, 86% of that, or a 14% drop, would bring it down to 29,198. The power consumption of my outdoor unit seems to be off. The printed information for the outdoor unit lists the operating current at 15.8 amps with an outdoor temperature of 104. Now I had a power monitor that I had connected to the input power circuit to the outdoor unit, and it indicated the following. And incidentally, I mentioned this is at my final test on the unit, and it indicated the input power of 2359 watts with a voltage of 234.8 and a current of 11.33 amps. The printed literature for this series outdoor unit lists the operating current for the 2-ton unit at 11.3 amps. For the 2.5-ton unit, it lists the operating current at 12.5 amps. And again, the 3-ton unit was listed at 15.8. Is it possible that either as a mistake in the factory or a subsequent switch out of compressors have occurred, and my unit actually has only about maybe a 2.5 ton? The current power consumption would suggest that. However, I have not been able to identify this compressor. The label on it has long since been bleached out by the sun. It does look a little bit like a Copeland, but still I haven't been able to identify it for sure. Well, thanks for watching. I'm interested in any comments that you viewers might have, and perhaps you can point out where my missing capacity is at. What have I overlooked? Thanks again. See you next time.